Welcome to the next lecture on derivatives. So, in the last lecture we studied about the exponential function and then we calculated the derivative of the exponential function. Today we will learn about the logarithmic function, which is the inverse of the exponential function, and then some other things. Let us start by recalling exponential function. So, this is written as exponential of x or e to the x. This is a function whose domain is, so this is from R to R plus, which is same as the positive real line. So, domain is the set of real numbers, range is all positive real numbers, and also we have that the exponential function, this is strictly increasing function. That means that if x1 is less than x2, then e to the x1 is less than e to the x2. So, from this it follows that, so this function x going to e to the x is an injective, which is also called one to one function, injective function from the set of real numbers onto the set of positive real numbers R plus. Now, suppose f is any function from some set x to y is an one to one and onto function, then we can define the inverse function which is denoted by f inverse. This is a function whose domain is y and the codomain is x. So, we have inverse function f inverse from y to x. This is simply taken as, so we have f inverse of y is equal to x if and only if f of x is y. So, to know the inverse of y, we need to look at the value of x for which f of x is y, right. And because this is a one to one and onto function, we know that there is a unique x. For every x here, we know there is a y in y, and because this is one to one onto function, the image of two different x cannot be the same y. So, now for every y here we look at the x such that f of x is equal to y, and then f inverse is the map from y to x. So, this is the general thing that you must have learned in function, that inverse of a function can be defined if we have an one to one and onto function. So, now for f x is equal to e to the x, we know that this is an 1 onto function from x is the set of real numbers onto the set of positive real numbers. We can define the inverse of exponential function which is called the logarithmic function, and is denoted by ln of x. So, this is also called the natural logarithm of x. So, log of x is nothing but the inverse of exponential x. So, if I write y is equal to ln x, this is equivalent to x is equal to exponential of y. Now, what are the properties of logarithm of x? So, first thing, what is the domain? Domain is r plus, that is ln x is this is not defined for x negative or 0. So, for x less than equal to 0, this is not defined. Ln x is defined only for all positive real numbers. Range of ln x is the set of all real numbers. This is because the exponential is defined from r to r plus, and another property is that this ln of x is also an increasing function of x. So, if x1 is less than x2, then ln x1 is less than ln x2, and just like we had the limit. So, what is the limit as x approaches positive infinity of ln x? This is equal to positive infinity, and the limit as x approaches 0 from the right side of ln x, this is equal to negative infinity. This is because limit of e to the x as x approaches positive infinity is positive infinity, and limit of x approaching negative infinity of e to the x is equal to 0. Therefore, the limit as x approaches 0 from the positive side of ln x is negative infinity. Let us try to draw the graph of ln x. And let me also draw the graph of e to the x. So, the exponential function, we have seen that the graph looks like this. At x equal to 0, this is 1, and as x increases, e to the x keeps on increasing, goes to infinity as x goes to infinity, and it goes to 0 as x goes to negative infinity. Now, what about log of x? This is the inverse of exponential x. So, the inverse of a function, the graph of the inverse of a function can be plotted by taking the mirror image of, this is the line y equal to x. So, you look at the mirror image of the graph of f of x in the line y equal to x, that gives the graph of f inverse of x. So, what happens is, this is the graph of log of x, looks like this, and the value here is 1. So, ln of 1 is equal to 0. This is because we know that exponential of 0 is 1. So, this passes through the point 1 comma 0, and as x increases, this keeps on increasing. Note that ln of x, this is positive if x is greater than 1, and ln of x is negative if x is less than 1. And of course, ln x is defined only for positive x. So, it is undefined for x less than or equal to 0, and this goes to negative infinity as x is going to 0 from the right. Previously in school, you might have learned logarithmic functions. So, let me compare this ln x with, you might have learned log of x before. So, how is log of x is defined? So, recall that if I write y is equal to log of x, this is equivalent to saying that x is equal to 10 raised to power y. So, to find the log of anything, you write the number as the exponent of 10. So, for example, if I ask you what is log of 100, so this is equal to 2, because 10 to the power 2 is equal to 100. So, this is analogous to, we also here we saw that y equal to ln x, this is same thing as x is equal to e to the power y. So, instead of 10, we are using e here. In general, we can define logarithm to the base b by, if I write y is equal to log x to the base b, this is if and only if x can be written as b to the power y, and we take this b to be any positive real number and b is not equal to 1. This is because if I take b equal to 1, then 1 to the power y is always equal to 1. So, if you take the function 1 to the power x, that is the constant function. So, we cannot define the inverse of that, but if b is any positive real number other than 1, then b to the y can be shown to be a 1 to 1 function, and then the inverse is the logarithm of the function to the base b. So, formally a to the power x for a bigger than 0 can be defined using the exponential function e to the x as follows. So, a to the x is nothing but the exponential of x ln a Okay, so, the exponential function e to the x we have seen what it is, and for any other exponent we can define a to the x is equal to e to the x ln a. Note that ln a is well defined as a is a positive real number. Okay, now let us see some other properties of log. So, one is that the logarithm of product x times y is equal to sum of the logarithm. And logarithm of x by y, this is equal to ln x minus ln y. This is if x is greater than 0, y is greater than 0. Again here x greater than 0, y greater than 0, and logarithm of x to the power any m, this is equal to m ln x. Here again x is positive. So, these properties you must have seen for the common logarithm to the base 10, and these are true for the natural logarithm also. This can be proved because to show this you have to show that the exponential of the left hand side is equal to the exponential of the right hand side. So, proof of 1 say. So, let a is equal to ln x and b is equal to ln y. Then what is x? X is equal to e to the power a and y is equal to e to the power b. And then we have to find what is ln of x times y. So, what is x times y? x times y is e to the power a times exponential of b, and we have seen that the exponential has the property that exponential of a times exponential b is equal to exponential of a plus b, and therefore, what is ln of x y is equal to a plus b. The logarithm of natural logarithm of any quantity is the exponent that occurs in e to the power this. So, this is same thing as a is ln x, b is ln y. Similarly, others can be proved. Another property which is important is suppose you have some other base. So, if I write log of x to the base b, this I can express in terms of the natural logarithm. So, this can be written as ln x divided by ln of b, and note that this is defined for b not equal to 1. So, ln b is non-zero. Note that ln b is not equal to 0, since b is not equal to 1. So, any logarithm to any base can be converted into natural logarithm. So, it is enough to study natural logarithm, and then we can deal with logarithm to any base b. So, this again one can prove. Suppose let me write a is equal to log of x to the base b, and let us write m is equal to ln x and n is equal to ln of b, then x is equal to b to the power a, also x ln x is equal to m. So, x is equal to e to the power m, and b is equal to e to the power n. Now, we have x is equal to b to the power a. So, we have e to the m which is equal to x, and x is equal to b to the power a, but b is nothing but e to the power n raised to power a, which is equal to e to the power n a. This implies m must be equal to n a, because e to the x is a 1 to 1 function. So, m is equal to n a, and then what we had to prove is that this quantity was a is equal to log x by log b, that is m by n. So, this implies a is equal to m by n, that is a is log x to the base b is equal to ln x divided by ln of b. So, now we will try to find the derivative of ln x. So, remember that we have seen that using chain rule we can calculate the derivative of the inverse of any function if I know the derivative of the function. So, we will use that to calculate the derivative of ln x. So, let y is equal to ln of x. So, we want to find dy by dx, but we know that this implies that then x is e to the power y, and because we know that we know the derivative of exponential function. So, we can differentiate this expression with respect to x. So, d by dx of x is equal to d by dx of e to the y, and this implies this is 1 is equal to, now here we use chain rule. So, this is d by dy of e to the y times dy dx by chain rule, and the derivative of e to the y is same as e to the y times dy dx, but e to the y is equal to x. So, this can be written as x times dy dx, and this implies dy dx is equal to 1 by x. So, what we have got is the derivative d by dx of the function natural log of x is equal to 1 by x, and because ln x is defined only for x positive, this formula is for all positive real number x. We can define also, if we replace x by mod of x, the absolute value of x, then ln of mod x, this is defined for all x except for 0, because mod x is always a non-negative real number. So, if x is non-zero, then mod x is always positive. So, log of mod x can be defined. Can we calculate the derivative? What is the derivative of f x equal to log of mod x? So, if we see f x is log of mod x, this can be defined piecewise as this is equal to ln of x if x is greater than 0, and this is equal to ln of minus x if x is less than 0, because for x greater than 0 mod x is equal to x, and for x less than 0 mod x is equal to minus x. So, this is the function. Now, we know the derivative of ln x. So, for x greater than 0, f prime x is equal to 1 by x we have seen, and for x less than 0, f prime x is d by dx of ln of minus x. Now, this again we can use chain rule, and this is equal to the derivative of ln of minus x with respect to minus x, which will be 1 by minus x times the derivative of minus x with respect to x, d by dx of minus x, which is minus 1. So, this is again equal to 1 by x. So, d by dx, the derivative of log of mod of x, is also equal to 1 by x. This is true for x belonging to any real number except 0. So, when you learn about antiderivative or the indefinite integral, there you will see that in the formula the integral of the antiderivative of 1 by x is written as log of mod x and not just log of x. So, okay, now let us look at a few examples. So, now we know the derivative of log x also. So, we can look at some example involving log. So, suppose f x is equal to sine of ln x, then what is f dash x? The derivative, we use chain rule. So, derivative of sine gives me cosine, cosine log x, and then the derivative of log x with respect to x gives me 1 by x. So, this is true, and of course, this is defined for every positive x. Let us look at one more. G of x is equal to cosine of log x plus e to the x. Again, this function is defined for all x greater than 0. Then g prime x, again we use chain rule. The derivative of cosine will give me negative sine of log x plus e to the x times the derivative d by dx of inside function is log x plus e to the x, and then this is equal to minus sine log x plus e to the x. The derivative of sum is sum of the derivatives. So, d by dx of log x gives me 1 by x plus d by dx of e to the x is e to the x. So, this is the derivative of g of x. Let us also calculate the derivative of a to the x, where a is any positive real number. So, let us see, a to the x we know is that this is defined as the exponential e to the power of x ln a. So, d by dx of a to the x is equal to d by dx of e to the x ln a, and now we use chain rule. The derivative of this will be equal to e to the x ln a times the derivative d by dx of x ln a. Now, here natural log of a is a constant. So, d by dx of x times ln a is simply equal to ln a. So, this is equal to e to the x ln a times ln of a, and e to the x ln a is equal to a to the x. So, d by dx of the derivative of a to the x is equal to a to the x times natural log of a. You can see that in particular, if I put a equal to e, then ln of e is equal to 1. This gives me the usual formula, d by dx of e to the x is equal to e to the x. There is another way of also doing this. So, what you do is that you write y is equal to a to the x. Now, take natural log both sides. This implies ln of y is equal to x times ln of a. This is because ln of a to the x we know is x times ln a, and now differentiate this with respect to x. Therefore, d by dx of ln y is equal to d by dx of x ln a. Now, here because y is a function of x, I can use chain rule. This implies this is equal to 1 by y times dy dx is equal to ln a, which implies dy dx is y times ln a, which is a to the x ln a. So, this gives the same answer, but it might be slightly easier for you to write in this form. Okay, so, next we will see that this second way of doing this can be done more generally, and we will discuss what is called the logarithmic differentiation. So, suppose we have a function f of x which can be written as some function u of x raised to power v of x. So, previously it was y is equal to a to the x, here u of x is just the constant a and v of x is the function x, but now we are allowing both these to be a function of x and we want to find f prime x. We want to find the derivative f prime x. Then we do the same thing as we did for the previous example. So, we take natural log to both sides. So, we have ln of f x is equal to ln of u x to the power v x, and we know by the property of logarithm this is same thing as v x ln of u x, and now we differentiate both sides with respect to x. So, differentiating with respect to x, we get the derivative of natural log of f x will give me 1 by f x times f prime x. This is again by the chain rule, and then the derivative of v x times ln of u x, here I can use product rule, this is equal to d by dx of v x ln u x, and this is equal to v prime x times natural log of u x plus v x times the derivative d by dx of ln of u x. This is by the product rule, and then again we use chain rule to find the derivative of ln u x is 1 by u x times u prime x. So, this is equal to v prime x ln of u x plus v x times 1 by u x times u prime x. So, this implies f prime x is equal to f x times this quantity here, that is v prime x ln u x plus v x by u x times u prime x, and f x is nothing but u x to the v x. So, we get the derivative of f of x in terms of x. So, let us look at some examples. So, first one we will look at f x is equal to x to the power of sin x. Then we take log ln f x is equal to ln of x to the sin x, which is equal to sin x ln x, and then we differentiate this. This implies 1 by f x times f prime x is equal to the derivative of this will give me cos x log x, and then plus sin x times derivative of log x is 1 by x. This implies f prime x is equal to f x, which is x to the sin x, times cos x log x plus sin x by x. So, note that you do not need to remember the previous formula for the derivative of f x, you can just follow the steps and then calculate the derivative. Let us see another example. So, here what we have is, now we have an implicit equation. So, find dy dx if y to the x plus x to the y is equal to 1. So, now here note that we cannot directly take log of this, but separately if you see, these are the exponents. So, what we can do is that you let u to be the function y to the x and v is equal to x to the y. Then we can calculate what is du by dx. Then what is given is that, then the given equation becomes u plus v is equal to 1. Therefore, if I differentiate this, du dx plus dv dx, this is equal to 0. Let me call this equation 1. U is equal to y to the x, this implies ln u is equal to x ln y, which implies if I differentiate with respect to x, I get 1 by u times du by dx is equal to the derivative of this with respect to x. Derivative of x with respect to x gives me 1 times ln y plus x times the derivative of ln y with respect to x. So, that is 1 by y times dy dx, and this implies du dx is equal to u, which I can again write as y to the x times ln y plus x by y dy dx. So, let us call this equation 2. So, since v is equal to x to the y, ln of v is equal to y ln x, and now we differentiate this to get 1 by v dv dx is equal to, the first term here is y. So, dy dx times ln x plus the first term times the derivative of second term ln x gives 1 by x. So, this implies dv dx is v, which is x to the y, times this is ln x dy dx plus y by x. This is equation 3. Now, using 2 and 3 in 1, we get the value of du dx and dv dx, we get y to the x ln y plus y to the x times x by y dy dx. This is du dx plus dv dx gives me x to the y ln x dy dx plus x to the y times y by x. This is equal to 0. Now, we want to calculate what is dy dx. So, these two terms we can combine. This implies, and then you see we have y to the x divided by y, which can be written as y to the x minus 1. So, this is x times y to the power x minus 1 plus the other term is x to the y ln x, x to the y ln x times dy dx. This is equal to the negative of y to the x ln y plus the other term is x to the y divided by x. So, this is x to the y minus 1 times y. So, this gives dy dx is equal to negative of y to the x ln y plus x to the y minus 1 times y divided by x to the y minus 1 y to the x minus 1 plus x to the y ln x. Right. So, we have calculated this. As an exercise you can try. One is cos x to the power y is equal to cos y to the power x. Find dy dx. Another is find dy dx if y to the x plus x to the y plus x to the x is equal to a to the b, where a and b are constants. Right. So, both these you can do in the similar way. You let this to be u, this is equal to v, then you calculate. Here you can even directly take logarithm both sides and then you can differentiate it, but in the second example you can take these three terms to be u, v and w and then find what is du dx, dv dx and dw dx, and then we know that the sum is a constant. So, the sum of the derivative will be 0, and from that you can calculate what is dy dx. So, this logarithmic differentiation is an important tool to calculate the derivative of functions when it looks complicated to calculate. Another thing we will learn about is what is called the derivative of functions when x and y are given in some parametric form. So, we want to calculate derivatives of functions in parametric form. So, let us assume that x and y can be written in terms of some parameter let us call t, that is x is a function of t and y also is a function of t. Then we want to find dy dx. So, to find dy dx, if you look at, since y is a function of t, if I write dy dt, this can be written as dy dx times dx dt, this is by chain rule, and therefore, this implies that the derivative dy dx can be calculated in terms of the derivatives with respect to t. So, this is the formula for the derivative of y with respect to x in terms of the derivatives with respect to t. So, dy dx is equal to dy dt by dx dt, or this I can also write in as y prime t by x prime t. So, you can calculate the derivative by finding the derivatives with respect to t rather than trying to solve for y as a function of x. So, as an example, if I take the equation of circle x square plus y square is equal to a square, can be parameterized as x is equal to a times cosine t and y is equal to a sin t, because we know that cosine square t plus sin square t is 1. So, x square plus y square is a square. Now, if I want to find what is derivative dy dx, so we know that dx dt is minus a sin t and dy dt is equal to a times cosine t. So, therefore, to find derivative dy dx, this is nothing but dy dt by dx dt, which is equal to a cosine t by negative a sin t. So, a cancels and I get negative of cotangent of t. Right. So, we get the derivative here in terms of the parameter t. So, that finishes today's lecture. In the next lecture, we will see some more examples of derivatives in terms of a parameter, and then we will look at some of the applications of derivatives. Thank you.